Okay, so subspace clustering algorithms, actually, once again, they've tried to find all clusters in all subspaces restricted to axis parallel subspaces, and they usually employ bottom-up search strategies. Yeah, so yeah, they are extremely similar to, or analogously to, the branch and bound feature selection approaches. They start with one-dimensional subspaces or subspace clusters and then merge them to compute higher dimensional ones. Yeah, so it's extremely similar, absolutely similar to these branch and bound feature selection methods. Typically, these approaches here in subspace clustering transfer the problem into a frequent item set mining problem, like the branch and bound feature selection methods also do. We might recall from KDD1 or from the subsection on branch and bound feature selection that in order to apply these branch and bound algorithms like a priori or FP growth, we need monotonicity. And in that case, in this case where we want to cluster, we need the monotonicity of the cluster criterion. Yeah? So the cluster criterion must be monotonic, meaning that if the criterion holds for a k-dimensional subspace S, then it also holds for any k minus one-dimensional projection of S. So in terms of features, if I have a k-dimensional feature space, if I just remove one feature, the clustering criterion still holds, which probably makes sense, because if I have less features, the similarity in absolute values shrinks, yeah, decreases. But we will have an example right away. And of course, the a priori algorithms and all that stuff use the reverse implication for pruning. So if the criterion does not hold for a given k minus one-dimensional projection of S, then the criterion does also not hold for S. Yeah? So it means that if we have some projection where the clustering criterion does not hold, any super space of this projection, so adding additional features to this projection does not yield any subspace where the criterion holds. Yeah? So in that case, we can prune all higher dimensional projections that can be, or that has this k minus one dimensional projection here as a subspace. Yeah, there are several approaches that do not rely on monotonic cluster criteria, and in that case they use other search heuristics. For example, best first, like in the feature selection section, best first, greedy search, random search, things like that. So this monotonic property, also called downward closure property, is very important for applying branch and bound. So it's more or less a scalability issue rather than anything else. Yeah, because only if I have a downward closure property, I can apply these pseudo-efficient things like a priori or stuff like that. I mean, a priori in the worst case still has 2 to the power of d, but so it's still exponential, but at least it structures the search space pretty good. And if the criterion is quite selective, we will have a good opportunity to find or to compute only the necessary candidates in a branch and bound matter. Yeah, but we will see that later on. Yeah, or just recall those branch and bound feature selection methods. So an example for such a downward closure property is a very simple cluster criterion, that of dense grid cells. Yeah, so I can compute, of course, in a grid-based clustering approach. I usually apply a grid on my data space. So I partition my data space in cells, and I say if a cell C of a given side length contains more than m points, it represents a cluster. This is a kind of density-based model because I specify the volume by the length of the grid cells and the minimum number of points I want to find in that grid cells. Yeah. And then I can compute, of course, dense grid cells, and I can merge neighboring cells to bigger clusters and stuff like that. So that is actually grid-based clustering, which is a density-based cluster model. Yeah, and this cluster criterion of grid-based methods, this cluster criterion is actually monotonic, that fulfills the downward closure property, because if C, the cell C, contains more than m points in a subspace S, then this cell also contains more than m points in any subspace of this subspace S, in any projection T of S. And here is the example and the counterexample. So here is the example where C, the cell C here, for m equals 5, contains more than 5 points. Actually, it contains exactly 5 points. So greater or equal is typically greater or equal than m points. So this is dense in that case for greater or equal 5 points. This grid cell here, indicated by these black lines, of course, is dense. So if we project or if we take a look at the projection of this cell on this one-dimensional feature space made up by B, we find out that, of course, there are all of those 5 points are also in this cell, in this projection here, and there may be even additional points like this one here. So this cell here, or the one-dimensional projection of this two-dimensional cell, is dense if this one here is dense. And the same holds true for this projection, of course, because all those 5 points are in this range here, in this one-dimensional range of this cell here, and there may be some additional points also along this B-axis, of course. So this is the monotonicity, the downward closure property. If the higher dimensional cell is dense, all lower dimensional projections need to be or must be dense too. The inverse application is if a grid cell of length S, like this one here, this one-dimensional cell here along the A-axis, is not dense, so this only contains 4 points, all grid cells of dimension 2 and 3 and 5, 4 and 5 and so on can also not be dense. So even if I merge this one-dimensional interval with this one here to form a two-dimensional grid cell here, and this one here is dense, contains more than 5 points, but this contains only 4 points. So only 4 of those points here can be in this A interval. So this is the inverse implication of this monotonicity criterion. So if I have a grid cell which is not dense, any super cells in super spaces can also cannot be dense also. So from this cell here, I don't need to compute higher dimensional cells, because I know all higher dimensional cells that take this one here as one interval, that are made up by this interval along the A-axis, cannot be dense. And that can be used to apply a priori style branch and bound subspace search.